I'm gonna go quickly over the material that we've been through last time, and then take it from there and continue for this introductory part. So the target of the introductory part is actually to give you kind of one cut through all the stuff that we will study in the course, and then we will go back to each one of those and take our time understanding it in more details. So remember, our objective, as per the discussion that we had last time, was mainly to kind of give you an overview on what's the internet, what's a protocol, the network classification. So what's an edge, what's a host, what's an access network, what are the physical layer or the physical media. Then we'll discuss about the core of the network, performance, what do we use to measure the performance, security, and then we'll talk about the protocols and the different layers. There is part about history. I'm not going to address it in the lecture, but you have it in the slides if you want to kind of go through what was the history of the internet. So we are doing all of this and taking the internet as our example of communication network, okay? So the first part was kind of trying to figure out some terminologies. And in that part, we talked about what's a host, right? And then we talked also about, so that's an end node, a node that either sends or receives information, versus what's called an intermediate node, which is basically passing information, but it's not generating or absorbing information itself. There's also one thing to keep in mind, that all the applications are typically running on the hosts. They are not running on the intermediate nodes. So things like email, whether it's an email client or server, things like web service, things like video calling, audio calling, all these things, they are running on the hosts, the end system of the internet or of the network in general. We also talked about the links connecting the different nodes together, and we call these communication links. And they can have various ways. They can be physical cables, something like optical fibers or copper cables, and they can be actually wireless. So we don't see them, but we know that they exist. So the link between your device and the access point in this room, I don't see where is it? Yeah, over there, right? That's an existing physical link, but you cannot see it, right? You can feel its result or its action, but you cannot see it. And a most important parameter of any link is something called the bandwidth. That's sometimes they also call it the capacity, sometimes they call it the speed, the maximum speed on the link, right? Which is generally how many bits per second the link can carry. Okay, so it's in units of bits per second. How much information per second you can pass through the link. We call that the bandwidth of the link. Okay. We talked about the concept of packetization. So data is not being transmitted in the form of a continuous stream, but typically it's broken into pieces, collection of bits, right? Each one of those includes multiple bits. Okay. And we call that piece together a packet. Okay. And a packet typically has a particular length, which is the total number of bits inside that packet. A packet is typically broken into two pieces. One piece includes the information, and the other remaining piece, we call it the header. The header is some other bits added so that it allows controlling the flow of these packets, where they go, where they come from. So it includes something like addresses, what kind of processing they need to go through to reach from the source to the destination. So that part is called the header. And then there is the information, which is basically the data that you want to send. Okay. Okay. Now, in order to send data from a particular source to a particular destination, so if you want, for example, to communicate from this node to this node, right? There are two ways to define how the data will go from a source to destination. One way is you simply reserve a fixed path between the two, right? And whatever data you send, it will always go through this path, and it is reserved. So nothing else goes through this whole path except the data coming from this source to this destination. Okay? This is called circuit switching. Okay? The other option is you don't do that. For each packet that you need to send from a source to a destination, the packet goes, the first step is that the packet goes from here to this. And when it is inside this intermediate node, the intermediate node is gonna look at the header of the packet, particularly the addressees, and then based on some table information inside this intermediate node, so this intermediate node includes some kind of a representation of what's happening on the network. So each link, what is the available speed on each link, which link is connected, which link is congested, which link is broken, and so on, okay? And based on that, it will decide just the next step. So it will say, okay, this packet should go, for example, here, okay? And that's it, just the next step. Then the packet would go to the next node, intermediate node, and that intermediate node is gonna again test the header, and based on the table of information inside that intermediate node, it would go, okay, it would say, okay, based on the header, this should go to a particular destination, and my decision is it should go to this node. That's it, just one hop. And at each point, the same process happens until eventually the packet reaches its final destination, okay? Now, I will take your question, but just a minute, okay? Now, if this node is sending two packets, so one red, one blue, okay? And they are both from this source to this destination, it can happen that one of them is gonna go, for example, through this route until it reaches the destination, okay? And the other one, the blue one, might, for example, go through some other completely different route. Okay? So it's not necessarily that, even though these packets are coming from the same source, going to the same destination, they can take different paths based on the instantaneous decisions that are taken at each intermediate node, one hop at a time. Okay? This is clear? This is called packet switching. So this option where you decide for each packet by itself, and only at each intermediate node you just decide what's the next hop, this is called packet switching, okay? The other one, where you reserve a full path for the whole duration of communication between a source and a destination, is called circuit switching. And you can imagine each one of those has its advantages and disadvantages. We will study them in more details later. But for now, just to understand the concept. What was your question?
Doctor, we said like at each node it is being decided where to go to which node, to the
Which
next
link?
step.
Yeah.
Which link, yeah. So when it goes to the next step, does it change the header each
No,
time,
no,
or it
no,
has
no.
a reserve?
The destination and the source address stays the same. There are other aspects of the header changing, but the source and destination, they stay the same because they are the same. Okay? Any other questions? Yes.
Can you give us examples of like circuit and the packet switching?
Sorry?
Examples.
I'm not sure what do you mean. You mean example application, for example? Okay, when you are doing file transfer, for example, that's packet switching. When you are doing voice call, this is circuit switching. So for voice, the link stays the same, reserved for the whole duration of the call. But I'm talking about classical voice, not voice over IP, because voice over IP is a slightly different. It's a mix of both, okay? But voice, regular voice, that's circuit switching. Okay. Any other questions? Okay. Again, we went quickly last time over what's the internet. It's just a network of networks. So you have your home network, you have your institutional network, something like the university here. This is what you have at home. This is some mobile network somewhere, let's say in the downtown, a base station connected to a computer, a telephone, and maybe a car phone, whatever, okay? Or even infrastructure like traffic lights and stuff like that in smart roads and smart vehicle system, okay? Or smart transportation system. So that's, again, we call this an edge or an access network. These ones, and that's gonna come in the next slide, okay? Even though they differ in size, right? You can imagine that this is much larger and it carries much more information, like here inside the campus. And when we connect to the outside, we have really large number of users, a large amount of data. This is much smaller when you have the home. This is probably intermediate between the size of this one and the size of this one, which is the group of users that are connected to a particular base station somewhere, right? Using the cellular network, okay? All of these access or edge networks are connected to a core network. So this is called the core in different hierarchies. Typically, you connect to a regional or a local service provider, internet service provider, and then the different regional or local internet service providers. For example, here, this might be Ooredoo, for example. Double O. Okay? So Ooredoo is a regional or a local service provider. But let's say, for example, the different networks from Ooredoo, maybe from Bahrain Telecom, from Saudi Telecom, and so on, they are connected, for example, to a big service provider, a global one like, let's say, Orange in Europe, or something like Vodafone Global, not Vodafone, the local one, okay? So these are more global, they are more core, in terms like they are deeper into the core of the network. And then again, at the other end of the story, maybe when you reach some particular state in the United States or some particular province in Canada or whatever, you will go back to another local service provider, and that local service provider is going to take your traffic to some edge or access network, like a mobile or a home or an institutional on the other side, okay? So this is kind of the hierarchy across the internet. It's a network of networks. And we also mentioned what is a protocol. I gave this example in humans. So in order to manage a classroom, for example, where I communicate with you and you communicate with me, we have to have some protocol that says, for most of the time I'm speaking and you are getting bored. Sorry. Most of the time I'm speaking and you listen. And then if you want to talk, you either raise a hand or you kind of say, can I ask a question? And then I stop talking and I tell you, go ahead. Then you ask your question. I wait until you finish your question. And then I start answering the question, or I ignore it completely, whatever. I have the freedom to do both, right? No, I will always answer. So in that case, that's a protocol between us. The objective of this is to make sure that whenever one of us is trying to communicate, the other can receive the information. Because if we talk all of us at the same time, nobody's going to be able to capture any information, right? Same thing happens when you are talking about devices like hosts or edge devices connected to core or intermediate devices. When I talk to this access point for the Wi-Fi, there is a protocol that says, for example, this guy does something called listen before talk. So it starts first to sense the medium. Is someone else trying to talk to the access point? No, I cannot sense any signal. Okay, then I can start sending information, right? Now, if everyone else is doing this, then when this is sending information, all the other devices are gonna wait until the transmission finishes, and then when they discover it's finished, one of them is gonna try to access or all of them at the same time, which is the case of what's called collision, and then they have a mechanism to resolve this such that eventually one only succeeds quickly, not after a million years. Because if they all keep trying to talk at the same time, they will always keep failing, right? So there is a mechanism to guarantee that if this failure happens, it will happen only for a short duration of time. And then it's resolved and someone gets the medium. Again, we will describe this further in much more details when we go to study formal protocols for different types of networks. But for now, just to understand what's a protocol. It's a mechanism that defines two important things, the order, who talks when, right? And the other thing is the format. Again, to communicate with you, if I stand here and I start speaking Chinese while all of you understand Arabic and English, then nobody is gonna communicate with nobody, right? And when you talk, I will not understand you. When I talk, you will not understand me. So in addition to who talks when, there is also what kind of language we will speak. Similarly, how does the packet look like? What's the format of the packet? Where is the data? Where is the header? Where is the addresses? And so on. So there is pre-agreed upon formatting for the information transfer so that both parties or all parties can understand the information, okay? That is what a protocol is all about. You hear lots of names of protocols. So it's the 802.11 for the Wi-Fi, HTTP for internet accessing websites, hypertext transfer protocol, right? IP, internet protocol, TCP, transport control protocol, and many other protocols that you hear about every day. We will discuss some of the key protocols also later on, how they work and what are the internal details of those. Last but not least, related to the internet, there is a standardization task force called the IETF, and they produce the standards in the terms of documents called RFCs. Each one of those RFCs has a number, and it talks about a particular standardization of a certain part or a certain functionality over the internet. Again, we have addressed this last time, so this is not new. In addition to components of the network, of any communication network, so we talked about nodes or hosts, so intermediate or hosts, these are both nodes. We talked about links, connecting them together, right? On top of that, there's some service being provided by this particular part of the internet. So there is an email service or hypertext like web service or something like e-commerce or something like voice over IP, where you can do calls over Google Meet or old time Skype, or now you have other tools for voice over IP, even WhatsApp, right? There is messaging service like the WhatsApp and the other messaging methods. There is something like the social services such as Facebook, Twitter, LinkedIn, like Social Professional, other things like Snapchat and so on, right? So all of these are services provided over the network itself. So there is the infrastructure pieces, the connectivity and the nodes, and there is the services, and those services are provided by applications running on the hosts, okay? So the service is not provided by something running on the intermediate node. It's always provided by some software or application running at one of the hosts, whether that host is a client or a server, okay? Yes?
Well, this is a question about the server. Because sometimes there's a service in USA. So for order to have a good connection here, they have to have a server in Bahrain.
Not necessarily.
So let's say
Yes.
they have a server here.
Sometimes they do that, they localize themselves so that they become faster.
Yes.
So the service is distributed in many places, yes.
So now the place in Bahrain is like the host.
Yes, it's a server, it's still a server. يعني the difference between what we call a host and a server, both of them are hosts, okay? But when it is most of the time responding to requests and providing a lot of data or receiving much less, then typically this is a server situation. As opposed to a typical host where you send less data and you receive a lot of data, okay? Any other questions? Okay, now on top of that, nowadays, and that's not very recent, it's now like a decade old, it's not always the case that when there is a host connected to the internet, that this host is interacting with a human directly, right? It used to be the case in older applications of internet, so always the phone, there's some human using it, the iPad or the tablets, the laptops, the computers, there's always some human sitting on the other side, causing the information to be generated and consuming whatever information is being received, right? But this is not the case in the last decade or so, and that's gonna expand even more. Now devices are autonomously connected to the network, and sending and receiving information to each other without any human involvement, right? That type of connectivity is called the Internet of Things. So no human involved anymore. Your dishwasher is connected to the maintenance server, and whenever it reaches a certain point where it requires some maintenance, it will issue an alarm at the maintenance server, and then that alarm is gonna cause some dispatching of service to come to your home and so on. Like that connectivity between the dishwasher and the service server or the maintenance server is completely autonomous. Nobody is going and checking the dishwasher and then pushing a button so that it sends an alarm, okay? It's happening completely autonomously. And similarly, many other things like, I mean, the applications are almost infinite if you count them, including the toaster that you see over there. So these type of connectivities are characterized by two things. There is no human involved, so it's always autonomous. And the other thing is that it's typically with light connectivity. So there is not that much data exchange between the different nodes, but there is a large number of nodes. So it's kind of different from the typical connectivity that we used to have. Less number of end nodes, but much more data generated from each one. The future is going in the direction of, with the Internet of Things, is going in the direction of less amount of data per node, but the number of nodes is going to explode. So it's every single thing, okay? Nowadays, my fridge is doing this at home, my dishwasher, my washer, my stove, my toaster, everything is, right? They are communicating one way or the other, and they are all connected through my Wi-Fi at home. And when I look at how many nodes are there on the Wi-Fi, it's too much. There are only 3 computers at home, but lots of connectivity, even light bulbs, they are connected through my Wi-Fi, right? So that you can control their brightness and all these colors and all this stuff, right? So that's a different era. And by the way, towards the end of the course, we will have a couple of lectures talking about this type of networks, the Internet of Things, and the progress happening so far in that direction, okay? This slide is describing what I have mentioned already earlier, what's a protocol. The slide is here more formal, but I've already discussed this with you earlier. So you see the definition of a protocol. It defines format and order of messages, send and receive, right? So who talks when and the format. And then also associated with that, it also defines if there are certain actions that needs to be taken in response of the exchange of the information. So like the example of the maintenance server. So for example, raising an alarm. That's an action that has to happen as a result of a certain type of message exchange, okay? This slide is important. So this really carries some tool that we need to learn. The way we describe protocols, we use something called time sequence diagram, okay? And the time sequence diagram is what you see here. For example, on the left side, it's describing a protocol of communication between 2 humans, okay? So you meet a person and you want to ask him or her about the time. So the first thing in the protocol of communication, you greet them. So you say hi. Now the protocol of human communication says if you greet someone, typically, if they are nice, they should reply back to you with greetings as well. So that person says hi. Then you ask the question, got the time means do you know what's the time or can you figure out what's the time? And then when you ask that question, you get an answer for that. So that's a protocol of communication described in a time sequence diagram. What are the components of the time sequence diagram? 2 important things. Something here called the actors, or the parties that are communicating together, the parties that are talking to each other, okay? So these are called actors, okay? And then there is the exchange of messages that happens, which is represented by action, and then a corresponding action, and then an action corresponding, sometimes an action followed by an action followed by an action, and then one response. It depends on what's the protocol, okay? So these are the actions that happens between the actors or the parties, the messages that they exchange together, the information that they exchange together, okay? And Notice that the vertical direction represents time, even though it doesn't have a scale. That's why we have these lines, not horizontal, but slanted. So this means that from the time I say hi until the other party receives and understands it, it takes a little bit of time. So there is some delay. It's not happening in 0 time. Okay? So the vertical direction is time. Okay? Now, taking it from the human to an actual communication protocol, for example, the TCP. So for TCP, whenever you are issuing some request from your computer, it just doesn't send the request immediately. Like for example, when you type the address of a website and then you press enter, it just doesn't immediately send that address of the website. It starts by communicating to the server that you are trying to talk to by sending something called TCP connection request. So I ask the server, can I connect with you? That's how the protocol works, okay? So it's not just sending the information immediately. Can I connect with you? And then if the server is available and it has capacity, it will reply saying yes. So TCP connection response positive, so active, connect. It allows you to connect. Then when it says so, you start sending, okay, I need this page from your site, a specific page on the web server, and it will reply to that by sending you the content of the page so you can see it on your screen. Okay? Yes?
For the first line of the TCP, or the first 2 lines, this includes the, like, making sure this is an authentic user.
We are not showing authentication.
But I'm saying it includes that.
It can include that in, but here we are just showing the simple one, not with the authentication and verification of these aspects. In that case, you will have several messages exchanged, not just the connection request. Okay? But yes, you're right. Typically, when you connect with something, you need to make sure that's part of the network security. You need to make sure that you're connecting with legitimate center, not just
Just like we did in the secure communication.
Yes.
So the server, does it contain all the files, images, everything of that website, or does it ask the host?
No. The server is a host. Remember, a server is just a host, but it's kind
build
of
a website.
full of data, and it's typically responding to requests. A typical host, which is not a server, is your node, which is typically sending requests and receiving content. Okay? So, I mean, yes, to answer the first part of the question, all the information related to that web service as a whole, that web address as a whole, is contained in the server. Now, this server is not necessarily in one, as Suhaib mentioned earlier. Not necessarily that it's just one device in one location. It can be distributed across, nowadays it's a cloud, right? So it can be distributed across many geographic locations. And it can be also replicated in many places. Which one is responding to you is something handled internally. But for simplicity now, we are talking about one-to-one. Okay?
I know this is for simplicity, but what other requests that you can send? Like here is saying, go to this at like get HTTPS whatever. But can you send like other sort of commands?
It depends. I mean, if for a web connection, this is the command that you want to send, right? But probably you are connecting to that server with TCP still, but you are asking for a file download. That's a completely different command, right? Or you are connecting to that server and then you are asking for watching a video, like YouTube, right? So that's a completely, it's not just simply a web page, right?
Okay.
It's a flow of contents, right? So that's a completely different command and so on. Okay?
Doctor,
Yes.
in the timeline, we can have multiple protocols. It's TCP and it's going to HTTP.
Yeah.
So
Okay.
interaction between protocols.
Yes.
One protocol.
Yeah, it's again, you mean, okay, yeah, it depends what you look at. So typically when we draw this, we are looking at a particular layer, right? The HTTP is kind of the application layer, right? While the TCP is something called the transport layer, okay? So typically when we look at a protocol, we are just more interested in what happens at a particular layer of protocol, so a single protocol. Part of what we will do here, so we are just saying here get this, and we are saying it was sent, right? From a TCP level, this is what's happening. But if you look at HTTP, HTTP includes lots of details. So when you send a page request, there's some other detailed exchange that's happening, but we're not addressing it here. Okay, we are only looking at, from a TCP point of view, I asked for something, it got delivered to me. What happened internally for that to be delivered can be addressed at a different level. Okay? So when we talk about network layers, probably this part that I'm trying to describe right now will become clearer. How we can, at any point in time, abstract the connection at a particular layer. And we don't care about what's happening below until we get up here. We just assume that these two things can talk to each other somehow. Even though to talk to each other, they have to go through all the lower layers, right? But the nice idea about layering is that we can only focus on layer-to-layer communication at the same level without caring about what happens underneath, okay? So you understand the concept of time sequence diagram? We will come back to this concept when we start studying formally the different protocols, and you will be asked to, after describing a protocol, you will be asked to kind of sketch the time sequence diagram for that particular protocol, okay? So keep this tool in mind. We will use it a lot through the course, and it's a very important tool to kind of describe as well as design protocols, okay? Okay, I think the next slide also is something that I talked about a lot. So it talks about the division of the network into edge, right? So we have those periphery networks, we call them the edge networks, right? This one. And we have the central ones, the internal ones, we call them the core network components, okay? So just conceptually, how we divide the parts that includes the hosts, and the first level of connectivity of the host is called an edge network. The part that includes only interconnection between different networks, we call that the core of the network, okay? Just so that when you hear the statement, you know what's the difference between both. Now for the edge network, sometimes also they give it the name access network. And in that case, they are kind of referring to that it allows you to access the internet or to access the core through that edge, right? And they also focus, when they talk about access networks, they focus on the physical connectivity or the physical media connecting things together. So they talk about wireless access network, wired access network, optical access network, and so on. So the focus is more on how the connectivity is happening in the edge network, okay? So again, the term access network and edge network can be used interchangeably, but generally speaking, when we say access, the direction is we are more focused on what technology is connecting those nodes at the edge network, okay? Yes?
So these wireless and communication links are within itself or with the edge network, within the edge?
Yes, so all of these, for example, are happening in an edge network. We have some wireless, we have some wired stuff. Even here also we have a mix and so on.
Doctor,
Yes.
so the area around the so called the edge itself?
The area? No. That network is called the edge network. For example, the network inside Qatar University, this is an edge network. The core in Doha would be the network, the starting from the end of the campus here, and starting from the end of your home, and starting from the end of every other company and other university, right? That connectivity that takes it from those, what we call edge networks, to the connectivity inside Ooredoo, this whole thing is called core network, right? So Ooredoo, with its network, until it reaches the end user. The end user is a university, the end user is one home of someone, the end user is a company like Qatar Energy or whatever, right? So those end users, they exist in edge networks. They are connected together through the core network. And that core network is not just Ooredoo, that includes also the global core network, right? So it includes the bigger service providers in Europe, connecting all the countries or all the continents together, okay? Yes?
And your core network is like the transmission line for the Wi-Fi.
Is like what?
The transmission line
For what?
for the network itself.
Uh,
The ones that connect.
it's why transmission line ما فهمتش.
No, like, it's not connection.
الكور نتورك دي is composed of many routers but they are bigger and none of them is connected to a computer.
Yeah.
These routers are service provider routers, right? And they are all connected to other routers at edge. So they are connected to home routers, to university routers, so until before the home router and the university router, everything inside is a core network. Right? Everything that belongs to a certain entity which is using the internet is called an edge network. Right?
يعني الجهاز نفسه كانديفيدوال مش
لا الجهاز ده هوست، ده مش نتورك اصلا، ده جهاز اسمه هوست. النتورك عباره عن هوست كونكتد مع بعض ومع انترميديت نودز عن طريق لينكس، سواء كانت اللينكس دي فيزيكال كيبل او وايرلس. يس.
So doctor, let's say like a node that's connected to hosts, it's an edge. But a node that's connected to other nodes, that's core.
اوكي تاني ليه انا بقول لك مش شرط؟ لانه فور اكزامبل هير اتليست الاكزامبل هنا واضح يا شباب. I didn't say it's a break, so relax. Okay, so here for example this is an intermediate node. It's connected to other intermediate nodes, but again this node is Qatar University router, right? And then Qatar University as a whole campus has a big fat line which is optical fiber cable by itself, not just one fiber but the whole cable, connecting them to some central point at Ooredoo. Starting from that central point with that fat fiber, right? This is where the core starts. And then you go deeper into Ooredoo network and then deeper into global service providers like the internet cable underneath the ocean, right? And then you go to another service, big global service provider in Europe. All of that is core, right? The edge is entities that are using the internet. Those entities might, Qatar University is an edge network, okay? Those entities might have their own intermediate nodes and their hosts. Core network does not have hosts, only intermediate nodes, okay? This is just an enlarged, so again, not much information added here, just an enlarged picture of a home access network or a home edge network. We call it residential as well, and it just shows you that even in a small residential network, you can still have varieties of connectivity. So you have wired here, you have wireless here, and typically everything, and you can have multiple intermediate nodes. So this is an intermediate one, this is an intermediate one, but typically all of that is aggregated into that Ooredoo router that they have next to your door, right, which is connecting you to the fiber, for example, and then that takes you after that to this takes you to the core. Okay? Yes.
الثلاجة متصلة بالنت يعني؟
الثلاجة عندي في البيت واصلة بالنت. واصلة على الواي فاي. يس.
بترن عليها بتقولها
لا مش انت اللي بترن عليها، ده هي اللي بترن عليا.
Connected through Bluetooth, no?
لا واي فاي. Mostly واي فاي. Most of the connectivity at home they all connect to the router. اسهل من انه كونكت لتليفونك، يعني تليفونك انت تقرب وتبعد ويختفي ويظهر. It's connected to the router على طول.
Victor, what features does it tell you the content?
We can discuss that later. When we come to the Internet of Things, we can talk about what are the uses of that. Okay. I didn't give you a break, so let. Okay, so this is just again this slide is just to show you that you can have, and we mentioned that earlier already. Okay, that you can have an access network as small as the one that we saw in the previous slide, which is a residential access network, or as big as the one that we see here. We call that enterprise or institutional access network, something similar to the access network, which is your home only, with a small router or a couple of routers, and a few computers and maybe some IoT devices, right? As compared to the access network here at Qatar University, which includes hundreds of routers, right? And lots of users, thousands of users, right? At home, you have maybe like 5 to 10 users maximum, okay? Both are access networks, even though they have extremely different scale, right? And the differences is gonna be number of users, speed, amount of information transferred inside those access networks between the large enterprise one and the small residential one. That's it, just to show you that the scale does not matter. It is still an access network, okay? Special attention is paid to wireless access networks, networks that rely mainly on wireless communication. Those ones have a special attention because they actually provide more flexibility. You can add users whenever you want without the need to like lay down one more cable or dig the ground and do a change to the infrastructure. And also by the nature that wireless communication is a broadcast communication medium. So whatever you send, if you want, everyone can listen to it. So you don't need to send over multiple links for multiple parties to receive your information. It's one link, everyone listens to it, okay? So that's an advantage and a disadvantage because it has challenges in security, but that's a different aspect we'll talk about later. Anyways, because we pay more attention to wireless networks due to their widespread and nice desired features, there is another classification for wireless networks in terms of size. A small network that covers a range of 100 meters to maximum a few hundred meters, we call that local area network, LAN, L-A-N, okay? While another one that covers an area with diameter in the range of kilometers, we call that a wide area network, WAN, W-A-N. So we have L-A-N, and we have, this one is abbreviated WAN, wireless area network, not necessarily access, wireless area network, okay? There is something defined in between, which is called metropolitan area network, smaller than the wide, but larger than the local. But most of the time, we put our networks in one of those two categories, local or wide. The MAN appeared at some time as a definition, and then it's much less used. So typically, you can either say that this is a wide area network or this is a local area network, okay? And the range, as I mentioned, few kilometers and above, that's a wide area network. Few hundreds of meters and below, that's a local area network, okay? Now let's look at this interesting discussion, okay? If you have a packet, okay, which has a total number of bits equal to L bits, and you want to send it from one node to the other, right? This is definitely not gonna happen in 0 time. So the transmission of that packet, we call that the packet transmission delay, takes some time. How can we calculate that time? If I know the size of the packet and I know the bandwidth or the speed of the link, what's gonna be the transmission delay? So the packet has a length L bits, okay? And it's being carried over a link. So this packet is being transmitted over this link, right? With L bits. And the link allows a transmission rate, a speed of transmission, R, which is measured in bits per second, okay? So what is the transmission delay? What is the time that takes the full packet to be transmitted over the link?
Distance and speed.
L over R, right? The number of bits divided by how many bits per second you can transmit. This will give you the duration to send the whole packet. We call that transmission delay, okay? So the packet transmission delay, which is defined here, okay, as the time needed to transmit the whole packet through the link is equal to the length of the packet divided by the speed of the link. Okay, or sometimes we call that the bandwidth of the link, or sometimes we call that the capacity of the link. It's the same thing, right? When we talk about networks. Okay, now.
Doctor, if I know that each bit, for example, take 1 second, so if I have 10, I multiply 10, divide by 1 second, so all of it take 10 seconds. Why is it divided?
يعني ايه each bit takes 1 second؟
To be transferred?
فهو ايه اللي هيخلي each bit to take 1 second to be transmitted؟ هو ده هو اصلا لما تقول each bit takes 1 second to transmit ده معناه ايه؟
يعني
معناه ان السبيد بتاعت اللينك دي is 1 bit per second. هو that's the definition of the speed that we talked about, right? So these two views they correspond exactly to the same thing.
ايوه انا هضرب بقى مش ناسي.
تضرب ايه في ايه؟
هضرب ان انا عددهم 10 في ثانيه في كل
ما هو انت each bit takes 1 second عشان الرقم 1 بس هو اللي سمح لك تعمل كده. each bit takes 1 second ده الانفرس بتاع الريت. You are talking here about the duration of a bit, which correspond to a link that has 1 bit per second. لو كانت each bit takes 2 seconds كان هيحصل ايه؟
هضرب اثنين
حلو. والترانسميشن ريت بتاع اللينك دي كان يبقى كام؟
1 على
1 على 2 فهي هي. So you are not doing something different, okay? It's the same thing. Just you look at it from a different perspective, but it's the same thing, okay? Going back to this. So, for example, let me give you a numeric example and see. Okay, it's easy, but let's say that I have a packet which has a length equal to, okay, 8. يلا. بلاش 8 equal to 10 kilo byte. Okay, and I have a link speed R equal 80 bits per second. Okay, what is the time to transmit this packet?
slow.
قول بس كام؟ هو سلو بس قول لي كام، عايز الرقم. كالكوليت. ها
125 second.
1 125 second. حسبتها ازاي؟ قول الارقام. ها so L is what؟ 10,000 يعني times 10 to the power 3 كده. اوكي وبعدين انا عارف انه غلط. بايت. So be careful about that, huh? Yeah, so this L is actually what? 8 times كام؟
لا 1024.
ايوه لانه الكيلو for the digital is 1024 1024 مش 1000. ما تنسوش دي. So كيلو ميجا is 124 times 124 وهكذا. Okay? So don't forget this as well. Okay? We are dealing with digital and bits. So the kilo here has a slightly different meaning, and also you have to pay attention to bits and bytes. Okay? So this is equal to 8 times 10 times 1024. This is the length of the packet. And then you have the R, which is again 80 without anything else. Now divide those two numbers. You get what? 1024 seconds, right? So that's a very long time, as you said, right? It's gonna take more than 1,000 seconds to transmit because it's a very slow length. Okay? خلاص؟
20 دقيقة.
Yeah, so what I wanted just here is to get your attention to bytes and kilo when we deal with bits. Okay? So don't forget you have to differentiate between bits and bytes, and you have to keep in mind that a kilo in the digital domain is 1024. It's not just 1,000. Okay? It's 1,024. ماشي يا شباب. Okay, this is the only slide that we will talk about physical layer. because you studied all the details of the physical layer in your communication course, signals and systems, and electromagnetics. Between those three courses, you have taken all what it takes about physical layer. So you have studied what happens when you try to transmit a signal across a cable, when you studied waveguides and transmission lines in electromagnetics, and what happens when you want to send that signal wirelessly, when you studied propagation in free space in electromagnetics as well. Then you looked at the communication aspect in the physical layer, things like how you change the frequency, what is the bandwidth of a signal, how can you change, convert a signal from analog to digital and from digital to analog, so sampling and reconstruction. All these you have studied them between your signals and systems and your communication course, right? You studied the modulation, how to bring it up in frequency, bring it down. All of these are the things that happens in physical layer. So we are not gonna spend any more time on physical layer, except just going through what are the different types of connectivities from a physical perspective. There are two types. There is guided transmission and unguided transmission. Guided transmission is all the cable system. Unguided is the wireless communication. So this is the two main categories, okay? Guided and unguided. Now under the guided, there are many types of media, 4 categories, right? Or 3, okay? And 1 different. So there is something called twisted pair, 2 wires twisted, right? Similar to what you do for electricity. You use the same type of cabling, 2 wires isolated, twisted around each other between the source and the destination, and they start sending the information across that wire.
Why do we do that?
Sorry?
Why do we do that?
Why the twisting or
Yeah.
why what?
Yeah, why do we do that?
Electromagnetics. Because this gives you better properties in terms of lower capacity, lower inductance, and then you can reduce the delay. So your signal, which is typically one like sharp going up, down, will not spread a lot. But that's a totally different aspect. I mean, that's a study in electromagnetics, right? So this is a transmission line. This is one type of transmission line, the twisted pair. And then you studied there that any transmission line has lump capacitance, lump inductance, and they affect lots of things like reflection, diffraction, all the behavior inside that guided media, okay? So this is one type. The other type is also composed of 2 wires, but they are geometrically different. It's called the coaxial cable, right? So there's a core and there is a shield outside. The shield is either solid, but again for flexibility and other stuff, the way they do it, if you look at the cable that comes from your dish to your satellite receiver, you will find that that cylinder is actually a mesh of very fine wires, causing it to look like a cylinder, but it's not a solid cylinder, okay? And then there is a core cable inside. Anyways, the concept is a shield and a core cable inside. That's called coaxial cable, okay? The third is quite different. So it doesn't have 2 wires, it's only 1 wire for higher frequencies, and it's called a waveguide. So you have something like this, or sometimes even cylindrical. There is nothing inside. So you inject the signal to this, and it travels inside the metal from one point to the other. Okay, there is no need for another wire.
It's like wireless, but
No, it's not wireless, guided. It's not wireless. This is wire.
It's
هو
not
كل دول بص يعني في الاخر انت درست في الالكترومagnetism. Even this, right? Your signal is actually traveling here between those two. تمام? So the existence of the metal is just to guide. It's not really where the signal is guided. Even though in circuits you study it as if it's the current and the voltage and the stuff. But for time varying signal, it's actually traveling in between the two metals. Okay? So the waveguide is another option of cable, and if you want to see a waveguide, look at your dish up there. There is the dish itself, right? The reflector. Okay? And then you notice something coming from here through kind of a metal, and then it finishes here with something that looks like this, right? This is called the LNB, low noise block, LNB, and this is receiving the signal. So your signal falls on the dish and then it reflects. It's a parabola, so it reflects everything to the center of the parabola, where it goes through this small cylinder, the LNB. And then after that, the signal is traveling inside this waveguide. At the end of that waveguide, there is a small converter that converts the signal from this type of transmission into the coaxial that goes down to your apartment or receiver down there, okay? So that's an example of a waveguide, but there are many other examples in real life, okay? So there are cables even at much higher frequency, not the one that you use for your dish, but if you go, for example, to Sat, if you have been to that trip, or maybe we can go to one, if you, most of you did not go, you will see that in their antenna farm, most of the antennas are connected through waveguides, not through coaxial cables or twisted pairs, okay? Someone had a question. Yes?
Fiber is the best cable, right? Or depending on the application.
Sorry?
Fiber
Fiber is a waveguide.
is the best cable, right?
Best cable? It depends. I mean, if you are using optical, then yes. But if you are using RF signal, which is not light, then it will not work, right? So it's useful when you are using optical. And if you go to optical, yes, it provides more speed. The nice thing about optical is that it provides more speed, okay? So that's, I said there are 4 types, right? And then I said 3 and 1. That's the 4th. The 4th is, again, wired connectivity, but it's optical fiber, this guy, right? And this is not composed of metal. It's composed of a non-metallic, non-conducting material. But again, it's a waveguide. It's only designed for the optical signal, which is a much higher frequency electromagnetic. So optical and RF, there is no difference between them, except that one is much higher in frequency, and accordingly, it has different propagation characteristics, okay? Okay. So again, this slide doesn't add much. It just talks about the 2 things that we mentioned earlier for wireless connectivity, the local area and the wide area, and adds to that terrestrial microwave links and satellite. Satellite, we know it, right? The guys traveling up there. Microwave links are wireless connectivity that carries large amount of information at higher speed, but it's only point to point. So it doesn't connect too many things together. An example of that would be, and it's just meant to replace cabling. Okay? Whenever you don't want really to kind of dig the ground and pay a lot of money to the infrastructure, and you want to connect 2 remote points together, the alternative to cable connection, if you don't have it, is the microwave link. Okay? It's a wireless connection, but it's only meant to come from one fixed point to another fixed point across tens to hundreds of kilometers. So it can reach a couple of hundreds of kilometers. Very nice, very efficient, but has one drawback, that in severe weather, like something like yesterday's weather, for example, the performance will degrade severely, because the signal at that higher frequency can be obstructed by things like a lot of water vapor, a lot of dust. Those 2 things can cause a lot of degradation. By the way, satellite communication also is prone to severe degradation when you have very thick clouds. And it happens in some of those days when you have really, really thick clouds, like thunderstorm and stuff like that, you don't receive the TV through satellite anymore, or it gets interrupted a lot, right? So again, satellite signal requires line of sight. Similarly, microwave link requires a line of sight. I'm gonna stop at this point because I don't want to exceed the time, even though we are a bit slower, but it's okay. We are only 1 slide slower